We are going to continue our discussion of inductively strong arguments by talking about two important notions from probability theory: relevance and independence. Recall that we have said that an argument is inductively strong when C is probable given P. That is, when the probability of C given P is high. And by is high, we mean that this conditional probability is greater than 0.5. So a natural question is this all there is to an inductively strong argument? Namely that P provides evidential support for C. Is there a condition that we're missing? Well, here's one. The argument is not deductively valid. Now, why would we want to rule out deductively valid arguments as arguments that are being inductively strong? Well, the reason is because of cases like this. Consider the argument with premise P and not P, and conclusion C. Now, this argument is valid, and the reason it's valid is because we can't find a truth value assignment that makes the premise true and the conclusion false. Because we can't find a truth value assignment that makes the premise true, because the premise, P and not P, is a contradiction. It's not true at any row of a truth table. If we were to evaluate the conditional probability, the probability of C given P and not P, using the ratio formula, this will be the probability of C and P and not P divided by the probability of P and not P. Now, the probability of P and not P, that is going to be 0, because there is no row of any stochastic truth table in which P and not P is true, so the probability that we're going to attach to this formula is going to be 0. So that means that this conditional probability is undefined. Now, since it's undefined, we have a little bit of leeway here. We could, in principle, say that this argument is inductively strong. However, notice C is completely independent of P and not P. So P and not P certainly may have absolutely nothing to do with C. So it would be odd to say that P and not P provides evidential support for C, because of course P and not P doesn't really provide evidential support for anything. So it's natural to say that an argument is not deductively valid. So an argument is inductively strong means that it's not deductively valid. But are we missing any further condition? Well, consider this example. So this is our running example. Every day so far this semester, Anne brought her laptop to class. Therefore, Anne will bring her laptop to the next class. So this is an inductively strong argument. The evidence, seeing Anne bring her laptop to all the classes so far this semester, does provide support, evidential support for this conclusion that she'll bring her laptop to the next class. What about these two arguments? Anne said that she saw Bob steal the laptop, therefore Bob stole the laptop. Or 10 eyewitnesses said that they saw Bob steal the laptop, therefore Bob stole the laptop. Does the premise provide evidential support for the conclusion in these two arguments? Well, in general, perhaps it does, but it really depends on whether or not Anne is a reliable or relevant witness to the fact about whether or not Bob stole the laptop. To take this idea even further, consider this argument right here. Bob, who is male, is taking a birth control pill. So therefore, Bob, who is male, is not going to get pregnant. And suppose this is a trial for some new type of birth control pill. And we want to, so the question is, can we use this premise as evidence for the conclusion? Well, the premise does provide evidential support in some sense for this conclusion. Why is that? Well, it's because the probability of C, that Bob is not going to get pregnant, given P, is going to be 1. It is equal to 1. So this conditional probability is quite high. So according to our understanding of evidential support, P does provide evidential support for the conclusion. But of course, the probability that Bob is not going to get pregnant is already equal to 1. So this premise doesn't provide any additional support for the conclusion, even though this conditional probability is already very high. And what's going on here? Well, the issue is that P is just simply irrelevant to the truth of C. So we're going to say that two formulas, phi and psi, are independent given a stochastic truth table, provided that the probability of phi is just equal to the probability of phi given psi. Said differently, there are an equivalent way of saying what it means for two formulas to be independent. One is, of course, this definition here is symmetric, so if the probability of phi is equal to the probability of phi given psi, then the probability of psi must be equal to the probability of psi given phi. Now, using the ratio formula, if the probability of phi is equal to the probability of phi given psi, now the ratio formula says this is equal to the probability of phi and psi divided by the probability of psi. If we were to multiply the probability of psi by both sides, we would get this formula right here, that the probability of phi and psi is equal to the probability of phi times the probability of psi. So these are three ways of saying what it means for two formulas to be independent. And intuitively, what it means to be independent is that if somebody tells you that psi is true, you don't gain any information about whether or not phi is true, or any additional information about whether or not phi is true. So, for example, suppose that you are flipping two coins, and let's P be true when the first coin lands heads, and Q be true when the second coin lands heads. So you're flipping two coins, P is true when the first coin lands heads, and Q is true when the second coin lands. Suppose that you flip it many times and you record the percentages of the four possible coin flips. So if you're flipping two coins, there are four possibilities. The first coin lands heads and the second coin lands heads. The first lands heads and the second lands tails. The first lands tails, the second lands heads, or they both land tails. Now, suppose that you record and you see 25% of the time you're in the first case, 25% of the time you're in the second case, 25% in the third, and 25% in the fourth. Now, we can see that P and Q, according to these probabilities in this stochastic truth table, P and Q are independent. If I tell you that the second coin landed heads, so we're in these top two rows right here, you don't gain any information about whether or not the first coin landed heads. The probability of the first coin landing heads is still going to be 50%. So the probability of P is equal to 50%. Since P is true in these first two rows, 0.25 plus 0.25 is 0.5. That is equal to 0.25 divided by 0.5, which is the probability of P and Q divided by the probability of Q. So Q is true on the first row and the third row. And that's just equal to the probability of P given Q. We can also see that the probability of P and Q, which is 0.25, is equal to 0.5 times 0.5, which is the probability of P times the probability of Q. So according to each of these three definitions, we see that P and Q are in fact independent. Suppose that you get a different stochastic truth table. When you record the percentages of how many times you got two heads or two tails or heads and tails or tails and heads, you got a different set of probabilities. So say 40% of the time you got P and Q both being true, so you got two heads, and 40% of the time you got two tails. Now, in this case, we see that P and Q are not independent. Why? Well, the probability of P is 0.5. P is true in the first two rows. The probability of the first row is 0.4, the second row is 0.1. 0.4 plus 0.1 is 0.5. However, if you were to learn that Q is true, so you restrict attention to row 1 and row 3. So restricting attention to row 1 and row 3, the probability of P is going to be 0.4 out of 0.5. So conditional on this extra information that the second coin landed heads, the probability that the first coin lands heads is actually 0.8. So this probability actually increases. Learning that the second coin landed heads gives you additional information about the first coin. Your probability raises from 0.5 to 0.8. And we can also see that by using this product formula. The probability of P and Q is 0.4. That is not equal to 0.5 times 0.5, because the probability that the first coin lands heads is 0.5. The probability that the second coin lands heads by itself is 0.5. So the product of those two probabilities is 0.25. So in this example right here, with this stochastic truth table, we see that P and Q are not independent. We're going to say that phi is positively relevant to psi if learning phi raises the probability of psi. That is, the probability of psi given phi is greater, strictly greater than the probability of psi. Similarly, we'll say that phi is negatively relevant to psi when learning phi lowers the probability of psi. That is, the probability of psi given phi is strictly less than the probability of psi. So now we have a third condition. An argument is inductively strong when P provides evidential support for C. So the probability of C given P is high, say greater than 0.5. The argument is not deductively valid, and P is positively relevant to C. That is, learning P actually changes the probability of C. It raises the probability of